So summary of what we have so far is basically our free body diagram, noting that W has been replaced by WY and WX. Normal force equal and opposite to the WY. In this case, the only force having a Y component in this particular case being the weight force, so that the normal force is simply equal and opposite to that. And we have a frictional force. We want to calculate the components of W from the information we have. We assume we know the angle alpha. Remember, alpha is the angle of elevation of the incline, which would be the angle of the x-axis relative to horizontal. And that angle, probably can't see it, but I put a little alpha right there, also occurs here, so that the angle of W as measured from the positive x-axis in the counterclockwise direction is 270 degrees minus alpha. So now, WX, I'm being a little loose with the notation because the quantity we get here is a scalar and I've got a vector on WX. I kind of qualify it at the end by saying that after we do this calculation, we understand that this WX vector is in the I direction. The WY vector that we get from the similar calculation being in the J direction. Let me adjust the camera just a little so we can see everything. Okay. Now, just applying what we should know now about the definition. As long as theta is measured from the positive x-axis in the counterclockwise direction, then the WX vector will be magnitude of W cosine theta. And this is actually going to be times the I vector, but we'll write it this way for now, which is magnitude of W times the cosine of 270 degrees minus alpha. If you know alpha, I think which on my sketch was something like about 18 degrees. Not sure that agrees with this sketch. You can subtract that angle from 270 degrees and take the cosine, and you'll get a perfectly good result. But it's worth noting that the cosine of 270 degrees minus alpha is equal to the negative sine of alpha. I assume you know enough trigonometry to understand why that's the case. You might have to draw the circular model and work it out a little bit. I'm not going to do that for you. If you attempt to work it out that way and are not able to establish why the cosine of 270 minus alpha is negative sine alpha, other than by maybe looking up a set of equivalences and quoting that, you should be able to work this out just based on pictures to see why this is so. If you can't do that, it's a good time to tell me what you have done, what you do think, and submit a question form. Ask me to clarify that for you. Okay, but you should work that out yourself. That's just something everybody, every engineer should be able to do. Everybody who does a physics course on the level of the university physics should be able to establish that. Also that the sine of 270 minus alpha is negative cosine of alpha. Okay, anyhow, we do that calculation either this way or this way. Doesn't matter. Comes out the same both ways. And then we multiply that result by the I vector. So that, haven't really written it out, but I'll put it up here. WX equals magnitude of W sine alpha times the I vector, and WY equals negative magnitude of W times the cosine of alpha times the J vector. I really don't want you to just memorize these as formulas. You need to understand why they hold. Okay, you need to try to clarify this because you'll retain it much better. You do much better if you understand the source of a formula and then apply the formula, other than just grabbing a formula. You're going to grab the wrong formula. You're going to mess up. you're much more likely to mess up. If you're really good at manipulating formulas, maybe not, but you're still not going to have the insight of understanding the source, which limits what you can do with the knowledge that you have. Okay, end of lecture on that. But and of course, the sine of alpha and the cosine of alpha could be replaced by the negative cosine of 270 minus alpha, which would give you this or this result for each of these. Now, the normal force in this case, being the case where the only force that we have that pushes into the y direction is the weight force, the normal force is going to be equal and opposite to the sum of all other forces acting into the incline. And that means in this case Fn is going to be equal to negative Wy. And we could then write that as magnitude of W cosine alpha times the J vector. You won't really usually need this form for the normal force. Okay, now the other connection is that the frictional force magnitude of the frictional force is going to equal a coefficient of friction times the magnitude of the normal force, and the frictional force is in the direction opposing motion. So here we have the magnitude of the frictional force, the direction of the frictional force. Now there's a little more to that. You could have a static coefficient of friction or a kinetic coefficient of friction, depending on whether, as happened in some of our recent experiments, the system just simply locks up and stays where it is. Then you have a static friction, or you have a kinetic friction. And there's another distinction to make. So I'm going to say that in the case of motion, and I could be more specific, the motion of two surfaces relative to each other, which is what brings about friction, the force of friction is equal to this. Static friction would be less than or equal to the coefficient of static friction times the normal force. Static friction can't actually, well, in some cases it can, depending on how the surface is moving, but static friction doesn't exceed what's required to maintain equilibrium. So there's a less than or equal involved there. We won't get into that right now, but I'll mention it. You're going to read about it. You probably, if you've kept up with your reading, you have read about it. Now, that means in this case, if the direction of motion is down the incline, then the force of friction will be in the opposite direction, up the incline. Should the motion be up the incline, the force of friction will be down the incline, and you simply have to deal with that in a case-to-case basis. I'll say again, I'll say now that this relates to the triangle analysis of the forces. In other words, we could make a right triangle here, and WX would be the opposite side of a triangle, where the side opposite an angle, the angle alpha would occur at this point of the triangle, or at this vertex of the triangle. And you'd have to keep in mind that WX is down the incline, because just analyzing the triangle won't tell you whether WX is this way or this way. Now, there's an advantage to that. I totally acknowledge and really kind of like the idea that makes you think about what's going on in a way that the circular model doesn't. You have to be conscious of the direction of WX in a different way than if you use the circular model. So there are advantages to that model also. And that's also the model you're going to see in your textbook. I stick with the circular model because it's simple, it's elegant, and it's less likely to cause errors. Although, again, kind of contradictory to my philosophy that you really ought to understand these things in your gut, and reconcile that as you will. Okay, anyhow, this is how you calculate these forces. You might want to do that. Let's just say that W is, let's say, 0.3 newtons, and alpha is 17 degrees. What would you get for these forces? And we'll even put a mu in there. Don't have a good place to write it, but mu K, coefficient of kinetic friction, is 0.02, which is probably about right for a Hot Wheels car, and also probably about right for the car that you drive. Most automobiles have pretty nearly the same coefficient of rolling friction. Yeah, and actually, I'm not going to distinguish between rolling friction and sliding kinetic friction at this point. Just say that the situations that we saw with the cars, you have effectively a coefficient of kinetic friction that's about 2%. So you might want to just plug those things in and see what you get for the 17-degree angle of elevation. Now, I don't think we had a 17-degree elevation on any of our setups, but it would be a good exercise, and I'll probably work that up in the upper right-hand corner in the next video.